Alright, in this video we're going to be talking about the properties of gases and the different gas laws. Alright, so some properties of gases that you need to know: that gases are easily compressed. That means you can take the particles and squeeze them very, very close to each other. Another thing about gases is with pressure. If you have a number of moles, or the amount, you have the volume and temperature. Those are all factors that affect the pressure of gases. One thing that you need to know about gases is what STP stands for. Oftentimes in our problems we're going to say STP. That stands for standard temperature and pressure. We talked about that once before when we were doing mole conversions. That looks nice. Alright, at STP the temperature is going to be 0 degrees Celsius or 273 Kelvin, and the pressure is at 1 atmosphere or 101.325 kilopascals. That's some great highlighting.
I do what I do. I can't see the thing on there.
That's all right. All right. So we're going to take a look now at some of the equations. We have Boyles Law, Charles Law, Gay-Lussac's Law, and the combined gas law we're going to be dealing with. Just so you know, whenever you see a 1, that's going to indicate the initial conditions. Whenever you see a 2, that's going to be when you have some type of a change. What are the conditions afterwards? Alright, so let's go ahead and let's take a look at the first gas law we're going to talk about. This is Boyles Law. Boyles Law is pretty simple. It's if you have a constant temperature, it involves the changes of pressure and volume. Alright, if you... I was like, what are you doing? If you decrease the pressure, what happens is the volume is going to increase. And if you increase the pressure, the volume decreases. So it's an indirect relationship. P1 is going to stand for the initial pressure. V1 stands for the initial volume. P2 stands for the final pressure, or the pressure that happens after you change the volume. And V2 stands for this final volume. Not writing that. Okay, you're not writing that. I see. Alright, so let's take a look at a practice problem in a second using Boyles Law. But let's take a look at this chart. This chart shows what happens if you increase or decrease the pressure. What does the volume do? So if you look in the center, where it's P1 and V1 right there, if you were to increase the pressure, that means squeeze the particles closer together, like in the cylinder right here. Oh, I can't do it. If you look at the cylinder, if you squeeze them down closer, what happens is you're shrinking the volume. And when you do that, it's causing a more force on the wall of the containers, causing the pressure to increase. If you were to raise the volume or increase the volume, what happens is you decrease the pressure. Okay? Anything else to add?
No, it's good.
That sounds good. All right, so now let's take a look at our example using Boyles Law. All right, so example 1. It says a sample of oxygen gas occupies a volume at 150 milliliters at 740 torr of pressure. What volume will it occupy at 820 torr? All right, so let's go ahead and start identifying what's going on in our problem. Oftentimes, the first numbers you see are going to be your P1s or your V1s, or the initial.
Look for keywords like initial or originally or starts or something like that.
Exactly. And usually the numbers that you see after or towards the end of the problem are going to be your final or your ending numbers. Alright, so my V1 is going to be 150 milliliters, my P1 is going to be 740 torr, and my P2 is 820 torrs of pressure. And we're going to be solving for what volume? So we're solving for V2. And just as a reminder, a torr equals a millimeter of mercury. So the thing here is it doesn't really matter what unit your pressure and volume are, as long as you're consistent with what it is on the other side of the equation. All right, so we're going to write down our So we're going to write down our equation. P1 times V1 equals P2 times V2. And are you going to be plug in the numbers. So you have 740 torr times 150 milliliters. Oh, those kids are noisy.
If you're running track, you were noisy running past our room.
Yeah, if you're running track,
shame on you.
I'm going to throw a stick in the hallway. Just kidding. And P2 is 820 torr, and you multiply that by V2. That's what we're solving for. So now you just say, well, how do I solve for V2? Well, you divide both sides by 820 torr, and that cancels out on the right-hand side. And you divide the left side by 820 torr.
We're basically solving a one variable equation here.
It's just like 7th grade math.
Word.
Okay, and if you notice that the units cancel out, torr and torr, and you're left with the unit of milliliters. So that's what unit we're looking for, because that's a volume unit. So you take 740 times 150 divided by 820, and you're going to get approximately, how many sig figs do you want here?
Should be 2, because in our problem here, the smallest number of sig figs we have is 2
sig figs. So you get about 135.365 milliliters, and to 2 sig figs, we're going to say about 140 milliliters. All right, so that's using Boyles Law. Okay, let's take a look at our second gas law we're going to be working with, and that's Charles' Law. All right, Charles' Law involves volume and temperature, and this is a direct relationship which states that if the volume increases, the temperature increases, and if the volume decreases, the temperature also decreases. Now, the key thing here is that your temperature, it needs to be in units of Kelvin. So if you have a temperature that's not in Kelvin, you need to add 273 to it to make sure it is. And also with Charles' Law, the pressure is going to be constant.
Oopsie. This is what. No. Not this.
Kelvin equals your degrees Celsius plus 273. In case you forgot, you have it. All right, so the equation is pretty simple. You guys will love this equation. Oh, you do the 0.15.
You don't have to do the 0.15.
Oh.
Anchor.
Being sophisticated over here.
It is honors. You don't have to do it, though. If you don't want to, you can just do 273. It's fine. MBD.
Anyways, with this equation, it's really simple because it's just proportions, and you guys love solving proportions. I can't talk. Cross multiply and divide. All right, so this picture right here involves kind of what's happening with Charles' Law. So when we do order the liquid nitrogen, you guys will love this, and you take a balloon and you put it in liquid nitrogen, what's going to happen is since you're decreasing the pressure, you should decrease the volume. And notice that the balloons are getting very small. So yeah, liquid nitrogen is like negative 300 degrees Fahrenheit. It's very, very cold stuff. Very, very cold stuff. And what happens is when you put that, the balloon will shrivel up really, really tiny because you're slowing down those particles. And when it warms back up, the volume increases again. Okay, so let's take a look at a chart that shows what's going on with volume versus temperature in Kelvin. Okay, so again, it kind of states that if you increase the volume, the temperature increases, or if you increase the temperature, the volume increases. Same thing if you decrease one of them. So that's a direct relationship. They're directly proportional. Okay, here we go with our example problem. So example number 2. It says, if a sample of nitrogen gas occupies a volume at 250 milliliters at 25 degrees Celsius, what volume will it occupy at 95 degrees Celsius? All right, so let's go ahead and identify our variables in the problem. And we know that V1 is going to be 250 milliliters. T1 is going to be 25 degrees Celsius, but we can't have degrees Celsius. You have to have it in Kelvin. So what we're going to do is we're going to add 273 to that, and you should get about 298 K. And we're looking for V2. That's what we're looking for. And we have T2, which is 95 degrees Celsius, plus 273, which is about 368 K. All right, so let's write down our equation. V1 over T1 equals V2 over T2. And let's plug and chug. So you plug in your numbers. So V1 is going to be 250 milliliters.
I don't have enough room.
Uh-oh, not enough room.
Man.
Won't move?
Oh.
Darn. It's alright.
Oh well.
Just right underneath. There you go. 250 milliliters, and temperature is 298 K. That equals V2 over 368 K. And remember, this is easy. You just cross multiply and divide. And when you do that, your units will cancel out, and the unit you'll be left with is milliliters. So when you do that, you should get your V2 as being, you get about, oh, you're plugging in your numbers. I'm like, what's going on?
You're a little ahead of me there, Chief.
I'm a little ahead. Okay. So you multiply those two together, 250 times 368 divided by 298, and here we go. We check the units. They cancel. Remember, that's how you do these problems. If your units cancel, you're doing it right. So we get V2 as being about 308.724, but to two significant figures, since all of our numbers are in two significant figures, we're going to round that to 310. All right, so you have 310 milliliters is our second volume.
Boom.
All right, here it comes. Gay-Lussac, or do you say Lussac?
Lussac.
I'm not French, so I can't say it right.
Lussac.
Yeah, good enough. All right, it's very, very close to Charles's law, except you change out volume for pressure. And what this says is, as the temperature of a gas increases, the pressure also increases if the volume is kept constant. Okay, if the volume or if the temperature decreases, the pressure also decreases. And the same thing as Charles's law, the temperature needs to be in Kelvin. So the equation is P1 over T1 equals P2 over T2. Okay, and let's take a look at this can. Now this is actually kind of fun to do. I forgot what the actual pressure is for when a can explodes. Do you remember, or the temperature? I can't remember. Anyways, this deals with aerosol cans. It says aerosol cans carry label warnings, do not incinerate or burn the cans or store them above a certain temperature. This problem will show why it is dangerous to dispose of aerosol cans in a fire. All right, the gas in a used aerosol can, that sounds odd, is at a pressure of 103 kilopascals at 25 degrees Celsius. That's pretty much room temperature. Not, yes,
it's close to standard pressure.
Close to standard temperature and pressure, but it's room temperature and pressure. All right, if the can is thrown onto a fire, what will the pressure be when the temperature reaches 928 K? All right. All right. So this problem, I forgot what the real pressure was. Darn it. Well, that's okay. So I think cans can only hold like 200 something ish kilopascals. So anything above like 300 kilopascals, those cans will rupture and explode. And you'll see what the pressure of the can is at 928 degrees Celsius. All right, so let's go ahead and add 273 to our degrees Celsius to get them into Kelvin. So you take, oh boy, this is a hard one. 928 degrees Celsius plus 273 is not 1201.
Whatever.
Yeah, there we go. 1,201 Kelvin. We have our pressure 1. We're looking for our pressure 2. So let's go ahead and write down our formula. It's a good habit to do, especially if you're going to be taking physics next year. Get practice writing down your formulas and then plugging in your numbers. And P1 is going to be 103 kPa. And T1 is 298 Kelvin. And that equals P2, which we don't know, divided by 1,201 Kelvin.
It's an ugly K.
It's a horrible K.
There we go.
It's a little bit better. All right, so what we're going to do is cross multiply and divide. So we're going to have 103 kilopascals times 1,201 Kelvin. And we're going to divide that by 298 Kelvin. And the unit should cancel out of kelvins. And we're left with the unit of kilopascals, which is the unit of pressure, and that's what I need. So P2, that equals, let's see, we got, how many sig figs we got? We got 3 sig figs. Still two sig figs. Okay, so we get about 415, which 2 sig figs, we're going to say 420. So we have 420 kilopascals. So that is a tremendous amount of pressure in that little can, and that's what causes it to rupture.
It's a lot.
A lot of pressure. Yeah, that would hurt us. I think it starts to crush us.
Yeah.
Yeah, we'd get crushed if we were under that
like
amount of
4
pressure.
atmospheres.
That's a lot. All right, here we go with our last gas law we're going to be talking about for the day, and that is the combined gas law, and it sounds just like what it is. It's combined all of our gas laws we're talked about. Boyles Law, Charles Law, and Gay-Lussac.
Gay-Lussac. That's not French.
Is it German?
I don't know.
Who cares? Okay, so so this shows what happens when you have pressure, temperature, and volume all together. Okay, and here's our problem. It says the volume of a gas-filled balloon at 30 liters at 313 Kelvin and 153 kilopascals of pressure. What should the volume be at standard temperature and pressure? Okay, so the first things listed, that is our V1, our P1, and our T1. And we're looking for what should the volume be. So volume V2 is what we're solving for, but it says since it's at standard temperature and pressure, we actually know what that is. It's a given. The temperature is 273 Kelvin, and the pressure is 101.3 kilopascals. All right, so we're going to write down the equation. P1 times V1 divided by T1 equals P2 times V2 divided by T2. And we are solving for, let's see, what are we solving for? We're solving for V2. So let's start plugging in our numbers.
That's all right. I mixed it up a little bit.
That's okay. That's all right. Good enough for government work. So we're multiplying our P1 times our V1. And we're going to divide that by our T1, which is 313 Kelvin. And we're going to set that equal to 101.3 kilopascals. And we're going to multiply that by V2, and we're going to divide that by our 273 Kelvin temperature. Okay, now we have to isolate the variable of V2. So what we're going to do...
Cross multiply and divide. Pretty much the same thing again.
Yeah, pretty much the same thing again. We're going to take 30.0 liters, multiply it by 153 kilopascals, and multiply it by 273 Kelvin.
Okay, so the 273 Kelvin goes up to the top, and the 101.3 kPa
goes on as you bought some.
All
right, and what you're going to do is you're going to divide by 313 Kelvin and also divide by 101.3 kilopascals. And if your units are correct, everything should cancel out except for liters. So you have kilopascals, Kelvin, they cancel out. The only thing left is the liters. You take 30 times 153 times 273 divided by 313 divided by 101.3, and you get about 39.5 liters, and that is our second volume. That's it. Deuces. Can I show you another way to help write this equation? Sure. So I find this helpful with the combined gas law. Oh, let's change colors. I'll pick this color, crimson for IU. All right. So I find this helpful sometimes, especially if you struggle with this variables. P1 V1 T2 equals P2 V2 T1. So what this does is it just brings this variable up here to each side, so it helps, and then you can just divide a little bit better. So that might help you a little bit in case you're struggling a little bit. I think that's it.
That's it.
All right.
Deuces.
Bye.